Hey, welcome to Beauty at Work. We're in between seasons at the moment, so check out this clip from one of our episodes. Does nature have a preference for symmetrical shapes? And if so, does that mean that beauty is a reliable guide to scientific truth? Here's what Oxford physicist Dr. Ard Louis had to say about this.
This is a project I'm working on for quite a long time. It was inspired by this question of how do these self-assembling systems work? How could you just randomly change interactions between things? How could you take a bunch of Lego blocks, randomly put glue down, and have it suddenly actually make something that works? And so I started thinking about what does evolution do? And evolution has really two steps. So first, there are mutations, or some kind of way that your genes are, your genotype, so your genetic material gets scrambled, gets changed. And then you get what's people call the phenotype, which is the physical manifestation of that change. So that's some property of the physical object. But DNA is not a blueprint, like a blueprint of a house. It's really like a recipe book, right? And the recipe is not the dish. So once you realize that some kind of process has to take that information, process it, and turn it into an output. So then I started thinking about, well, what's the simplest example we have of processing systems? They're actually computer programs, right? And so I thought, well, this step of evolution, this first step, which is generating new variation, is a little bit like randomly typing onto a computer program and then seeing what comes out. Once the phenotype exists in the population, then natural selection may select for it or not select for it, depending on whether it increases fitness. But that first step is really interesting. It kind of tells you what can happen. And then if you start, there's a very deep set of mathematical principles in theory of computer science that tell us that if you just randomly type programs in, you might accidentally, for example, type a program like print 01 500 times. Right? That's a short program, but it'll generate a sequence of length 1,000 01s. Right? So what that tells you is if you type into some kind of programming language, which is what the biology does, it randomly changes the genotypes, but the genotypes are not the outputs. These outputs get translated by some abstract language that I may or may not know. The argument is, if I look at the other side, I'm much more likely to see things that have short descriptions than things that have long descriptions. Because if I randomly type, I'm unlikely to type a correct program that's long, but I might accidentally type a correct program that's short. Does that make sense?
Yeah.
Yeah, so you're more likely to type short programs than long programs that are correct. And you can then measure that. And then so what I'm really saying is simple things, by which I mean things that have short descriptions, are more likely to come out of evolutionary processes than complicated things. And symmetry is actually quite simple. So if I want to make a complex, so we looked at protein complexes. Proteins are the molecular workhorses of your cell. Your cells are full of these proteins, and they form, all these molecular machines are made of proteins. So 2 of them make a dimer, 3 of them make a trimer, 4 of them make a tetramer, etc. And so you can look at tetramers or hexamers, sexmers, and you'll see that lots of them are symmetric. Now, it turns out that if you think about this as this kind of algorithmic process, what's happening is you're randomly adding and subtracting things on these proteins. If you want to make a certain shape, it's much easier to say, make this pattern and repeat it a bunch of times than it is to say, to actually specify where every single object goes. Right? So my print 01 500 times is like a symmetric description. I say something and then repeat it. Right? So the intuition is, since symmetric things have shorter descriptions than unsymmetric things, if I just randomly search in the space of algorithms, I'm going to first find the symmetric algorithms, the ones that make symmetric things, before I find the asymmetric ones. In fact, we can mathematically prove that for every extra bit of information I need to describe the process, I drop the likelihood of getting it by a factor of 2. So it's a very nice, beautiful law. And so what we did is we applied this law to protein complexes and showed that this explains the frequency with which you find them in nature. So people used to think, there's lots of symmetric clusters in nature because somehow symmetry gives you some advantage. We're saying, actually, no, it's simpler. It turns out that if you remember that you're searching in the space of the algorithms rather than search in the space of shapes, then you're much more likely to make something symmetric than something that's not symmetric. And what we see, and so what we then basically, we show this in some theoretical models, then we show it for real proteins, and for RNA, and for every other molecules. And this explains patterns of nature extremely nicely without having to worry about natural selection at all. It's not that natural selection isn't working. It's just that the reason for the symmetry is not natural selection, but the fact that symmetric things are easier to make. So it's as simple as that.
Right.
So that's the argument. So it's an algorithmic argument. At very, very high level, we're saying, just remember, evolution is searching in the space of algorithms, not in the space of shapes. That's how it does stuff. And once you realize that, it kind of opens up a very different way of thinking about what evolution is doing. And symmetry is just one of the consequences of that.
How do things like considerations of, say, efficiency or elegance tie in? Because it seems like a shorter program is also perhaps a more elegant program, right?
Yeah, so those are things that we're still thinking through. So, but there is an interesting link to Occam's razor, which I think. So Occam's razor is an idea that simpler descriptions are better. If you've got multiple descriptions, pick the simplest one. And so this is saying that evolution is basically picking the simpler algorithms rather than the more complex ones. And we often think of simple descriptions as being more elegant somehow. So it does link together. It's like nature has an automatic elegance builder in there. If you ask me what I think is elegant about the story is that these very abstract ideas from theoretical computer science have been around for a long time and have been, linked to a very different part of mathematics suddenly apply to life. I think that's the elegant part of it. That's not the same as saying nature. Well, nature does seem to prefer more elegant solutions in these systems than you might otherwise expect, and that's just built into the nature of the way evolution works.
Yeah.
I mean, this is quite a radical idea. Okay, this goes against the way that you're normally taught. And so I always recognize that extraordinary claims require extraordinary evidence. And so we're still thinking through, how far up the complexity chain these principles work.
Right. But your finding is that symmetry seems to occur much more frequently, significantly more frequently than you would expect, right? Is that?
Well, so we know that symmetry is more frequent.
Right.
And so the question is why?
Okay.
And the traditional way of thinking about that, there must be some selective advantage to it. So nature must try different shapes and see if the symmetric one ends up giving higher fitness. And what we're saying is actually no. The symmetric shapes are the first ones to appear. And as long as the symmetric shape is good enough to do the job, nature's going to pick a symmetric shape over an asymmetric shape. Okay,
so which then raises questions as to how to explain all the asymmetry, right? That we find,
yeah.
I know there are some physicists who have, I suppose, talked about maybe the bias toward symmetry in a different sense, perhaps the bias toward symmetry in theory, where there's a preference for more symmetrical theories. People like Marcelo Gleiser, I think, have argued that we should pay more attention to asymmetry, and because asymmetry is so vital for, say, time or just even our existence in the universe, right? I mean, I think if we had the symmetry we would expect, then there would be equal amounts of matter and antimatter and so forth, and that doesn't seem to be the case. So, what do you think is the sort of role of asymmetry in nature, and then in your argument as well? How does that relate to your finding about algorithms? Yeah. So what actually, if you look very closely at these protein complexes that we mentioned, they're all actually not perfectly symmetric, but slightly asymmetric. And there's some kind of more detailed reasons for why that is. And that's to do with the fact that if you make it perfectly symmetric, the bonds have a hard time satisfying themselves. So what happens is you go for the symmetric shape, and then it kind of just twists a little bit away from symmetry. And so what we're saying in that case is you've got almost symmetry, and then a little twist away from it. But it's still true that at its core, evolution is going to the symmetric, finding the symmetric solutions, and then deviating from it a little bit. Then in physics, we've got a very important concept called symmetry breaking, where you look at a system, you find it has a symmetry, and then you see that nature often breaks the symmetry, so it goes one way or the other way. And these are very important for,
biological molecules, if you just make them in your laboratory, there can be 50-50 different chiralities, left-handed and right-handed, whereas nature just uses one kind of the two. Yeah? And so they're left-handed ones. And so there's some kind of breaking of the symmetry there that was important. So I think there's something actually very beautiful about that as well, because you only can really think about the breaking of symmetry if you start from something that's symmetric. And it's important to remember that the number of asymmetric shapes you can make is always much, much larger than the number of symmetric shapes. There's only a few symmetric shapes and many asymmetric ones. And so the kind of asymmetry that physicists often look at, or biologists looking at, are often small deviations from symmetry or breakings of symmetry. You're still thinking about a very small subset of the space of all possibilities. And that still gives you, actually, there's kind of an aesthetics in the imperfection that's there as well.
Yeah. Well, that's fascinating. Another aspect of beauty I wanted to ask you about is the way in which beauty can either be helpful in theorizing or a liability. And so here I'm thinking about folks like Sabine Hassenfelder, who've argued that beauty has been leading physics astray, the pursuit of, say, beautiful equations and so on. Do you find this sort of, I'm just curious to know what you think of this. Do you find beauty as useful as a heuristic in your work, or do you find it, perhaps potentially misleading? What are your thoughts on this?
Yeah, I think that the problem is that when we talk about beauty, we often mean slightly different things. And so I remember there's a very famous physicist and then theologian who passed away a few years ago, John Polkinghorne, who was a student of Paul Dirac, who's one of the great exponents of beauty in science. And Polkinghorne once said, we recognize beauty when we see it. And although it's hard to define among physicists, he was a theoretical particle physicist, you kind of see it, you recognize it when you see it. So one of the issues there is that what Polkinghorne and other great theoretical physicists saw or understood is something that they've learned over time to recognize as being a sign of a good theory. Now, it's interesting that in the whole kind of the kind of history, the 20th century history of modern physics, oftentimes the solutions that ended up being successful were remarkably beautiful in the sense that they were very simple, often had high symmetries to them. And so one of the things that then happened is people started using this idea to go further and further. Perhaps the most famous example is Paul Dirac. So Dirac, in 1928, published a very famous paper where he looked at quantum mechanics, which is a theory of very small things. So it's Schrödinger's equation had just come out in 1926. It's a theory of small things, like electrons. And then connected that with special relativity, Einstein's special relativity, which is a theory of very fast things from 1905. And he asked a very simple question: if I have a small thing that also goes fast, okay, what will the equation look like? I know two different things that it has to, two different limits that it has to satisfy. But it turns out that if you take an electron and you try to make it obey the laws of Einstein, so-called Lorentz invariant, it's a symmetry that it needs to obey, that the only way you can make the equations obey that is by adding another particle to the equation. So that mathematics doesn't allow you to have an electron that does that without adding this extra object. And so he, being very mathematically oriented physicist, just published it, even though it seemed strange. And he later says that he just believed that particle was there. And a few years later, 1931, 1932, Carl Anderson at Caltech discovered the positron, which is the antimatter partner of the electron. And in that way, antimatter, which is this really crazy thing, it's the opposite of matter. You take electron and positron, you put them together, they annihilate into energy. So it's E is mc squared. The m from the two particles becomes E. We now use it in PET scans, positron emission tomography. So you go to a hospital, you can get these, they can use positrons. But they're a really crazy thing. And they were discovered in some sense by mathematical elegance, or the mathematics kind of imposed this on us. I remember as an undergraduate learning about this and thinking, well, this can't possibly be true. How could two completely disparate ideas, quantum mechanics and special relativity, put them together, and the only way you can make it work mathematically is if you have this other kind of object. So that's an amazing success of just our minds. It's an amazing success of what people call the unreasonable effectiveness of mathematics. And that success was then repeated many times in discovering other particles, all the way to we get where we now have the standard model, which is a model of all the particles that we've currently ever seen. And the Higgs boson was the most recent one that was found, but nobody doubted that it was there because it had to be there, because that pattern has just been repeated many times. And so what Sabine is trying to say is, well, how do you know that success is going to continue on if you try to go, because we 90% of our universe, we don't know what it's made of. It's dark matter. We've got gravity, which is a classical theory, and these quantum theories, we have no idea how to bring these together. So the problem is we're not getting experiments at the moment that are showing us where to go. And in that vacuum, what a lot of my colleagues in theoretical physics are saying is, well, we're going to take this kind of this Diracian approach, which is let's posit some kind of symmetry, and they take the mathematics and let's see what it tells us. And we're going to just do that again and again and again until we find something that works. And Sabine is saying, well, this is, to be honest, this is a process that's been going on for a long time. So I think the Higgs boson was predicted by Higgs more than 50 years ago. So that's a long time to not have, a new particle that we can find. And so it's perfectly reasonable to say, well, how do you know that this methodology is going to keep working? We don't know. It was astoundingly successful. It predicted antimatter out of nothing, just like fell from the sky. It's completely amazing. And that is very beautiful. So I often say the Dirac equation is as beautiful as the most amazing piece of music or the most amazing mountain range. It's as a piece of something extraordinary. It's beautiful both in the kind of sense of the sublime, because you just wonder, how can I see something about nature? And it's actually aesthetically beautiful because the equations are very simple. They have kind of symmetries to them. They're extremely elegant. So it's beautiful on many different levels. And it's obviously beautiful and amazing because it was so successful. But the fact is, we don't know why that methodology is successful. We don't know why we have this unreasonable effectiveness of mathematics. Obviously, it worked really well in the past, but maybe if we're not careful, it's constraining us from some very creative idea. So that would be, I think the pushback that Sabine gets from my colleagues is to say, fine. Show me what your new idea is then that's going to be better.
Right. So what's the alternative to relying on?
We're totally happy for you to critique us, fine, okay. But then show us what we should do instead. And that's where it's a bit problematic because nobody knows what else to do.
Right. I suppose if you're going to posit a hypothesis, you may as well go with one that's more beautiful than, I don't know if that's, because there isn't another criterion for. Yeah,
when these physicists, when they say they're using beauty as a guide, they really mean something more subtle than just aesthetics. What they mean is we're going to look for structures of mathematics because these structures of mathematics have explained to us where all these particles come from. So there's these symmetries groups, basically, and they have a certain number of objects in them, and then those are exactly the particles that you find. And in Dirac's case, there's a particular symmetry that he put in there, and that's what dropped this out. And so you can generalize these ideas again and again and again. And so that's what they're trying to do. So it's not just that they are. So basically, the beauty is that deep mathematical structures, often discovered by mathematicians in a completely different context, turn out to somehow impose their will on the physical world and allow us to see things that end up being true. And so the modern physics, my string theory colleagues particularly, are just pushing that same idea further and further and further. And so when Sabine says we shouldn't look at beauty, what she's really saying we shouldn't be looking for mathematical structures that the universe will then follow. And then the question then is, okay, what are you going to do then? And this is really hard to know.
Beauty at Work is brought to you by Templeton Religion Trust. If you enjoyed this clip, go check out the full episode. And please take a moment to subscribe and leave us a review. It really helps get the word out about the show. Thanks, and see you next time.